Here's a recap of what we've covered in simple harmonic motion so far. I'm not going to include energy concepts at this point for this video. Okay, so far we know that we have Hooke's law. Okay, basically the restoring force is equal to the opposite of the spring constant times the displacement. All right, and we also know Newton's second law, F equals ma. If we put the two together and solve for acceleration, we get the differential equation for simple harmonic motion, which is basically negative k over m times x. That negative sign just says that the acceleration vector is pointing the opposite direction of the displacement vector. I'm going to probably eliminate that negative sign after a while. The angular equivalent of that, the angular analog, we know that torque is just like F equals ma, torque equals I alpha. Okay, the moment of inertia times the angular acceleration. And analogous to Hooke's law here, where force equals negative kx, we could put torque equals negative k, but it's not necessarily a spring constant this time. It's kind of the angular analog of a spring constant times the angular displacement theta. Okay, if we put these two together, what we can solve for angular acceleration alpha, we get alpha is equal to negative k, which would be analogous to the spring constant, over I, which is analogous to the mass, the moment of inertia, right? And then times theta. All right. So we have, so far so good, using Hooke's law and F equals ma, and then we get our angular analog of that. So these are really important equations for simple harmonic motion. These are the basic equations for simple harmonic motion right here. Okay, this would work real well for a mass spring system. So say something like this, where you have a spring and then you have a mass, and let's say it's at there's the equilibrium position, and it's going to bounce back and forth on either side of the equilibrium position. Okay. There are also some trig functions that are helpful in understanding the motions, the simple harmonic motion. Okay, in terms of position of a simple harmonic oscillator, moving oscillator, we can say that the position is equal to A times the cosine of omega t, where omega is the angular frequency in radians per second, and t is time in seconds. If we take the derivative of that, we can get the velocity of the oscillator, the oscillating mass, and that would be equal to negative A omega sine of omega t. People who take calculus can easily see why that is. If we take the derivative of velocity, or the second derivative of position, we get the acceleration, which is equal to negative A omega squared cosine omega t. Okay, so these are the big three here. These are very important equations in order to predict what the position of an oscillating mass would be, what the velocity would be at any instant, and what the acceleration would be. Now, if we take this right here, and we take this, we can substitute. If we let me just put that in here, we have A equals negative k over m times x. Let's substitute this in here for A. Okay, and let's substitute this in here for x. All right, and what are we going to get? Well, we'll get negative A omega squared cosine omega t, substitute for A, right, equals negative k over m, and then x would be this, a cosine omega t. Okay, now we can cancel some things out. A cosine omega t, we have that on both sides. And we can multiply both sides by -1 to get rid of the negative sign. And then what we end up with is omega squared equals k over m. This is a very important result, and it's used all the time in dealing with simple harmonic motion. Okay? We can also write it like this. Take the square root of both sides, and we'll get omega is equal to, and we'll just take the positive value of the square root, square root of k over m. Okay, now omega here stands, like I said earlier, it stands for angular frequency. Okay, in radians per second. Angular frequency in radians per second. Okay. Now angular frequency is related to linear frequency f, that's in cycles per second, by this relationship here. Let me just say it this way. Angular frequency is equal to 2 pi radians over the total period, the time it takes for one cycle. There's a relationship between frequency and linear frequency and period. Linear frequency here. Let me move that up. Linear frequency f is equal to 1 over the period t. So here's the period. So if omega, the angular frequency, is equal to 2 pi over t, therefore omega is also equal to 2 pi, since linear frequency is 1 over t, 2 pi times f. So those are a couple of good relationships there. Anyway, we could substitute 2 pi over t in for omega here. So substitute in this for omega, and we can get 2 pi over t is equal to the square root of k over m. And then if we solve for t, the period, this would be for like a mass spring system, the period is equal to 2 pi times the square root of m over k. We'll just rearrange that, and we get this very important result. This is the period for a mass spring system, as I drew up here originally, vibrating back and forth. It could also work for a mass vibrating up and down. So this is a good one right here. T equals 2 pi times the square root of m over k. All right. The next thing I'd like to bring up is the idea of phase constant. If you remember, position is equal to a times the cosine of omega t, but that's only in the situation where at t equals 0, x is equal to 0. Okay? But at t equals 0, we might have it starting at a different spot. So how would that work? Well, we can use a circular motion analogy for simple harmonic motion, like this, and we can say that as a ball goes around in the circle, if we shine a light on the ball, it's going to cast a shadow on a screen right here, if this is the screen, and the ball would be going back and forth. So if the ball started right here, for example, and we're shining a light this way, the shadow would be here at this point on the screen. As the ball moves around in the circle, like that, the ball's on the screen, the shadow on the screen is going to go back and forth like this. Okay. Well, if at t equals 0, the ball happens to be right here with an angle of phi, let me draw that in with a finer pen, or phi, I don't care how you pronounce it, phi or phi. It's not theta, okay, in our example. Okay, this would be the phase constant. So the angle on this circle where the position of the mass is at t equals 0, that's your phase constant. So phi naught is equal to the phase constant. In other words, the angular position at t equals 0. Phase constant. So, how about at t? What if it's here? Well, that would be an additional amount, right? So this additional amount would be radians per second times time, okay, omega t. All right, so at t equals 0, x would be equal to a times cosine of omega t plus phi naught, but since t is 0, that drops off, and that's just equal to a cosine of phi naught. So at t equals 0, this is our starting angle. That's called the phase constant. All right, what about at t equals 1? At t equals 1, at position 1 here, at time 1, I should say, not t equals 1. At time 1, we'd have x equal to a cosine omega t plus phi naught. But this time, this is t, it would be t1 right here, and we'd have to figure out what that is. The whole point, what I'm trying to say is that that phase constant here causes a shift in the cosine graph. So, for example, this phase constant shifts the cosine curve to the left. If we have something like, for example, x equals a cosine omega t plus pi over 2 radians, so where phi naught is equal to pi over 2 radians, what are we going to end up with? Well, our normal cosine graph looks like this. I went too low on that one, but okay, where this is the x position here, and this is time. Okay, so we'll split that up into 4 sections. This is total time period. This is 1/4 t, half t, 3/4 t, and so forth. This is the negative maximum displacement or negative amplitude. Here's the positive amplitude. Okay, so that would be normal. Okay, but if we have a graph like this, x equals a cosine omega t plus pi over 2, this graph gets shifted over to the left by pi over 2 radians. So this phase constant here causes the graph to be shifted to the left. So if we imagine shifting that to the left, moving that whole thing over, moving this part here over to here, we'd end up like this, right? Let me just split this up into 4 sections again. Okay, so we'll end up with this. See? And then down like that. So if this would be the full time period. This would be 1/4, half, 3/4 time. So see how it got shifted to the left because of this phase constant there. Alrighty. So that's another important aspect for the AP Physics C students to know, that phase constant causes a shift to the left. Now let's look at what happens. Let's try to use our knowledge to figure out what the period is for a simple pendulum. Now, a simple pendulum is just basically a mass on the end of a string. So a point, we consider a point mass on the end of a string. So here's a point mass. There's a lightweight, like negligible mass thread or something like that with a point mass right there. Okay, and it's displaced a very small angle, theta, and it has to be a small angle in order to undergo simple harmonic motion. If the angle is too big, like if we move the mass way up here, as it's swinging down this far, it's not undergoing simple harmonic motion. Only when it reaches this point where the angle theta is small will it undergo simple harmonic motion. So that's an important aspect. Here's the length of the pendulum from the pivot point to the center of mass of that pendulum bob. Okay, I'll draw a force vector mg. That's the weight. And now I'll just split that weight vector up. Oops, I split that weight vector up into components. And the only component I care about is this one here, because that serves as the restoring force. So this is mg times the sine of theta. There's theta again, just like that one. Okay, so this is the important aspect right here. This component is the restoring force. It acts kind of like the force that a spring exerts on a mass spring system. But in this case, there's no spring. It's just this component, this part of the gravity component that causes the pendulum to swing back through the equilibrium position. Now this here, this little arc here would be, we can call it x. And that's just a small displacement the opposite direction. So if we move this out this way, as it's swinging out to the right, there's a restoring force acting on it to the left. And that's why according to Hooke's law, we have our F equals negative kx. Now remember, this is for small angles only, small theta only. So therefore, for small angles, the sine of a small angle is approximately equal to that angle. So this is an important aspect. So a simplification is called the small angle approximation. Okay, now let's take a look. We have Hooke's law, F equals negative kx. We see that the restoring force here is equal to mg sine theta, which we can simplify using the small angle approximation as equal to mg theta. Okay, and so we can substitute that in for F right here, a restoring force. So we'll substitute that in. Okay, and we get mg theta. All right, now I'm just going to use absolute values here and not worry about the negative sign. So mg theta then will let equal to kx. And what's theta? What is theta now? That's what we need to figure out. So let's look over here and rely on our unit circle ideas where S equals r theta, right? If we're dealing with radians. Now in this case, we'll use x for that. So that'd be x, and we'll use L for r. X equals L theta. Therefore, theta is equal to x over L. And we can substitute that in right here for theta. All these little lines, or arrows I should say. Okay, so that would be then mg x over L equals kx. Now we can see that we have an x on each side, we can divide both sides by x. And so we're left with mg over L equals k. Now if I divide both sides by m, we get k over m equals g over L. Okay. Now if you remember from the first page that I went over, let me just flash that back on here. Remember that omega squared equals k over m? Okay, remember? Okay, let's use that aspect here. K and substitute omega squared in for k over m. Okay, so let's that be omega squared equals g over L then. So that's just the gravitational acceleration divided by the length of the pendulum. Okay, now remember also that omega equals 2 pi over t. Okay, so let's take the square root of both sides of this. We get omega is equal to the square root of g over L. We'll substitute 2 pi over t in for omega. And so therefore we get 2 pi over t equals the square root of g over L. Okay, just rearranging it to solve for t, we get t of a simple pendulum is equal to 2 pi times the square root of L over g. And again, L is the length of the simple pendulum, and g is just 9.8 if it's on Earth, or 1.6 if you're on the moon, or whatever the acceleration due to gravity is at that point. Okay, so that's another aspect we need to think about. Now, there is something called a physical pendulum. I'd like you to know the period for. So let's go over a physical pendulum. A physical pendulum is one where you have, it's not just a string with a point mass on it. It actually has a moment of inertia that you have to take into account. It's a solid object that would be oscillating. And so let's go over that. Let me just draw, let's say, a cutout piece of plywood or something like that. So let's say this is a cutout piece of plywood. Here's the pivot point, that little dot up at the top. And let's say the center of mass of this cutout is right here. So I'll just label that X with a cm next to it for center of mass. Okay, the distance from the center of mass to that pivot point here we'll call D. Okay, now let's draw a force diagram here. The force can be thought of as acting, all of the weight can be thought of as acting through the center of mass. So I'll draw a vector there for the weight, and then we'll just make another vector triangle like I did for the simple pendulum, and this would be theta here if this is theta here. Okay, so far so good. So this is just the equilibrium position, and this is moved away from equilibrium by the angle theta. Okay, this little component right here is mg sine theta again. Okay, now we're going to use the small angle approximation again. Small angle approximation, which means that we're going to say that for small angles, sine theta is approximately equal to theta. Okay, we're also going to recall that F equals negative kx, Hooke's law, and therefore the angular analog of that would be torque equals negative k times theta, where this k is not the spring constant, but an angular analog of it. Okay, I also want you to recall that torque is the cross product of the position vector, in this case, well, r cross f if you want to, but in this case r is d here. And so, and that's equal to rf times the sine of the angle between. Now let's see what we have here. So therefore, if we, and the force is mg, so that'd be there, and and R is D. So I can just put that in here. So torque would be equal to D times mg times the sine of the angle between. Okay, but according to our small angle approximation, sine theta is approximately equal to theta, so I can just make this theta here. So this is D times mg times theta. So that's our torque. Okay, so I'll just circle that important result there. This is also an important result up here, so I'll circle this one. Okay, if we set these two equal to each other, we'll get d mg theta equals k times theta. Both sides have theta, so we can divide both sides by theta. They cancel out, and we're left with k equals mg times d. Now that k isn't a spring constant, but it is analogous to the spring constant for this physical pendulum. Okay, now we also need to recall another thing about torque, that torque is equal to the moment of inertia I times alpha, the angular acceleration. So if we combine this result here, let's call this, if this is 1, this would be 2, and let's say this is 3. Let's combine 2 with, and this would be 4 here, 2 with this, okay? And so we get torque is mg, remember, mg d theta, so I can just put that in, mg d theta for torque, substitute that in for here, equals I times alpha. Therefore, if we rearrange to solve for alpha, we'll get something good here, okay? So alpha, therefore, would be equal to wait a minute here. That's fine. Alpha is equal to mg d over I times theta. Now, if you look at this carefully, and compare it with our fundamental equation for simple harmonic motion, A equals k over m times x, basically, if we just treat the absolute value, we see that this is analogous to this, right? Okay. Now we already saw that this is a spring constant for a mass spring system, but this right here, mgd, is analogous to the k value for a simple pendulum. So this would be analogous to the k right there. And you know that I, the moment of inertia, is the angular analogy of mass. So this would be like k over m right here. And we know, again, that omega squared is equal to k over m from before. Oops, sorry, let me put that up here. So therefore, omega is equal to the square root of k over m. In an analogous way, for this, omega would be equal to the square root, since this is analogous to k and this is analogous to m, be mgd over I. So for a physical pendulum, that's the angular analog. Okay. Now lastly, we remember that omega is equal to 2 pi over t, the time period. So we can just substitute that in for omega and set that equal to the square root of mg d over I. And we can solve for t. T, therefore, is equal to 2 pi, if we just rearrange this, 2 pi times the square root of I over mass times gravity times that distance d. And this, my friends, is the time period for a physical pendulum. Thanks a lot, everybody.